To navigate an airplane safely across long distances, pilots rely on a two-dimensional representation of a three-dimensional planet. But taking a spherical object and flattening it onto a rectangular sheet of paper creates a mathematical problem. The surface inevitably tears, or it stretches. The Earth itself is not a perfect geometric sphere. It bulges at the equator and flattens at the poles, forming an oblate spheroid with a polar diameter roughly 23 nautical miles shorter than its equatorial diameter. Cartographers cannot translate this curved, irregular surface to a flat plane without sacrificing accuracy. Every flat map forces a compromise, distorting either the physical area, the true shape of the continents, the distance between points, or the angles. In aviation, angular distortion introduces critical errors. Pilots fly by referencing specific compass headings. If the angle on the map does not match the actual geometry of the Earth, a straight-line course plotted on paper will pull an aircraft miles off target. This diagram compares a direct great circle track against a rhumb-line track. The shortest distance between 2 points on the globe is the arc of a great circle, but maintaining that direct path across the curved surface requires a constantly changing heading. Flying a constant heading, a rhumb line, crosses every meridian of longitude at the identical angle, which creates a curved path across the Earth. Because the raw physical geometry of the planet resists being laid flat, safely navigating it requires a rigorously engineered mathematical projection. This image displays the physical line marking the prime meridian at the Royal Observatory in Greenwich, London. It is the designated starting point for the navigational grid at longitude 0 degrees, forming half of a continuous circle running through the geographic poles. The baseline for the latitude grid is the equator. Its plane sits exactly perpendicular to the polar axis, bisecting the oblate spheroid. Lines of longitude and the equator are known as great circles, meaning their planes pass directly through the center of the Earth. All other parallels of latitude are small circles, intersecting the Earth's surface without passing through its core. Aviation distance is derived from this geometry. 1 nautical mile equals exactly 1 minute of arc along any great circle. With 60 minutes in a degree, 1 degree of latitude will always equal exactly 60 nautical miles anywhere on Earth. The navigational grid functions as a direct mathematical translation of the planet's physical mass into measurable units of distance. Cartographers manage the compromise of a flat chart through a process called projection. You can visualize this by placing a light source at the center of a reduced wireframe Earth to cast the shadows of its grid outward. If the translucent cylinder wraps around the equator to catch these shadows, the resulting projection preserves angles but severely stretches the landmasses as you move toward the poles. To minimize this stretching, modern aviation relies heavily on the Lambert conformal conic projection. Instead of a cylinder, a translucent cone intersects the globe at 2 specific parallels of latitude. By mathematically slicing this cone and unrolling it, cartographers create a flat chart where the scale remains highly accurate, particularly between those 2 standard parallels. Charts built using this conic projection exhibit a property called conformality. Conformality dictates that angular relationships are preserved accurately across the entire surface of the chart. For a pilot, conformality ensures that plotting a straight line between 2 airports on the paper yields a geometrically true, flyable course in the sky. This is an excerpt from a VFR terminal area chart, illustrating how this projection encodes 3-dimensional topography onto a flat surface. The extreme density of information requires specific decoding. The thin lines tracing the terrain are contour lines. Each line connects points of equal elevation above mean sea level, plotted in 500-foot vertical intervals. To communicate rising terrain instantly, the chart uses hypsometric layer tinting. The background color steps from light green at sea level through increasingly darker shades of brown as the ground elevation climbs. Inside every mapped latitude and longitude quadrangle sits the maximum elevation figure. These bold 2-digit numbers denote the highest known terrain or physical obstruction within that specific boundary. Cartographers calculate the maximum elevation figure by locating the highest physical feature, then mathematically rounding up to the next 100 feet to provide a built-in safety buffer. By interpreting this topographical matrix of contour lines, tints, and elevation figures, a pilot establishes a minimum 500-foot vertical survival margin over threats they cannot yet see. The mathematical ratio governing how much physical Earth fits onto the paper is the chart's scale. On a standard sectional chart, the scale is 1 to 500,000. 1 inch of paper represents 500,000 inches, or roughly 7 nautical miles of actual terrain. Over sparsely populated regions, this ratio provides enough detail for visual navigation, but over dense urban environments with complex airspace, a 500,000 scale compresses too much data into an unreadable space. This chart excerpt focuses on the congested airspace around Montreal Pierre Elliott Trudeau International. It is a VFR terminal area chart, drawn at a 1 to 250,000 scale. By dedicating twice as much paper to the same physical area, the chart expands the detail for safer navigation. This map displays the global coverage grid of operational navigation charts. Designed for long-distance transit, they use a massive 1 to 1 million scale, stripping away minor landmarks to display vast stretches of continents and oceans. Scale operates as a strictly mathematical filter, adjusting the density of topographical detail to match the complexity of the airspace and the speed of the aircraft. Beyond physical terrain, pilots operate within a three-dimensional framework of controlled airspace boundaries and radio frequencies mapped directly over the geography. This chart boundary highlights the precise coordinate plotting system. The borders contain tick marks that separate the parallels of latitude and meridians of longitude into individual minutes of arc. Airport symbols dictate operational rules by color. Facilities depicted in blue operate with active control towers. Those printed in magenta rely on common traffic advisory frequencies, where pilots coordinate their own separation. Large graduated circles, known as compass roses, surround ground-based radio beacons. These allow pilots to plot specific magnetic radials to or from a navigational aid. This aeronautical overlay effectively merges the permanent physical geography of the planet with the invisible electronic infrastructure governing the sky. The chart itself is built on a grid aligned with true north, the geographic pole, but an aircraft's internal compass aligns with the Earth's magnetic field, which points to magnetic north. This dashed magenta line is an isogonic line. Cartographers print these on the chart to map the exact degree of magnetic variation present in a specific region of the globe. Pilots measure their initial course against the true north meridians printed on the map, then apply the isogonic line's value to calculate the actual magnetic heading they must fly. Physical distances derived from great circles are mathematically projected through a Lambert cone to preserve angles and encoded into a highly dense two-dimensional matrix. A VFR sectional chart is a finely tuned mathematical instrument, translating the geometry and physical laws of the planet into the operational reality of visual flight.